Hi there. Um, I'm Jules, presenting to you today. There's already quite a few people in the room, so I started the live feed already early. We're gonna wait a few more minutes. We'll kick off around 4 o'clock or just after 4 o'clock. See some names I recognize as well. Saber, hi Saber. It's some time since we last saw each other. Just checking. Carlos, sound, video is all good. Super. So we'll wait a little bit longer for the other attendees to arrive. And I see Mike there in the audience as well. Hey, Mike. Just yeah, one thing I can't influence. It's starting to become nice weather now in the Netherlands. So in the background, there's the light will come in and out. I could move a little bit. Maybe. No, it's okay. It's kind of okay. Hi, Klaus. Good afternoon. Thanks also for participating. Klaus has found the public chat. At any point in time, you can leave messages and questions as well in the public chat. Don't hesitate. And we'll wait a few more minutes. It's 3 minutes to the hour before we start with the live webinar. And for the replay users, later on, everyone actually gets a link to the replay, but also obviously the presentation slides. And if you're watching in replay, you can just skip this section. I always tend to start 5 minutes earlier to already welcome the people that are coming in. And there's a lot of people already coming in. Good afternoon, Ari. And Jasmine as well. Hey, Jasmine from the States. That's cool to see you too. A long time ago. So with me today are two moderators, Carlos and Arthur. Carlos Valladolid will be moderating as well as Arthur. So if you have any questions or issues with the live view, let us know, and we'll try to get that sorted as quick as possible, of course. It's a minute to go, so there's already quite a lot of people in there. I'm just going to wait a little bit longer, and then we'll kick off with the live webinar. Okay, it's here in Rotterdam. It's 4 o'clock sharp. So I'm going to start with the webinar. Again, everyone, welcome to this webinar hosted by UReason. Carlos is already in the chat sharing some of the instructions for when you have questions, when you would like to ask questions, etc., to make the experience of the webinar as smooth as possible. And before we start, a few important details. My colleagues Carlos and Arthur support me in the background today as moderators. If you have any questions, please feel free to contact them. And of course, if you have any thematic or technical questions, You can ask them during the presentation. Carlos will collect all your questions, and I will answer the questions all together in the Q&A session towards the end of the webinar. And if I see, because I have multiple screens for this webinar, if I see the questions popping up here in the public chat, I will also try to answer them as good as possible. So don't hesitate to ask questions. I'm keeping my eye on the public chat as well. And our webinar today is going to have a look at how you can turn data that you store and keep in your data historians, how you can use the data and make it of value, supporting you and your organizations in maintenance activities and optimization, process optimization. So let me start sharing the screen. When I start sharing the screen, the picture here will disappear. I'm still here, of course, presenting to you. And if everything is fine, you should see the screen, the starting screen. So let me first start by introducing myself. I'm Jules Oepmans, presenting to you today. I have a background in AI starting in the 90s, and I've been involved many times in the past 25 plus years in prognostic and predictive programs that ensure asset integrity for critical assets and critical processes. I've done this in different industries, such as oil and gas, petrochemical, chemical, and paper. And my work has always been focused around using the data that is available, both streaming and historical data, to provide better understanding of what is happening in the process, i.e. what is happening now, and what is expected to happen to the process and the assets supporting the process. On the slide here, my contact details. If you have any questions after the webinar, don't hesitate to email me. And just to point out again, everyone, all the participants and registrants of the webinar will receive a replay link as well as the slides. So you don't need to note down my contact details. You can also do that at a later point in time. And don't hesitate to reach out for any questions. So I work at UReason, a Dutch software company that provides solutions for real-time condition-based and predictive maintenance. And I help our customers daily to use our software, from data analysis to the setup of applications and solutions that monitor important assets and optimize processes. At UReason, we combine our domain expertise and software knowledge with our customers. And on a daily basis, I help our customers with starting very often from the business cases and the use cases, extracting the data and creating solutions. We have offices in Rotterdam, which we see here in the pictures, and in Reading in the UK. And our customers are predominantly in the manufacturing and process industry, and the majority of them are located in Western Europe and the North Americas. UReason is active in the field of real-time condition monitoring, predictive and prescriptive maintenance. And our field of operation is from helping customers to insights into data, to helping asset owners and OEMs and maintenance services organizations with data-driven maintenance solutions. Often we start together with our customers to define the business case and the use cases to focus on. And very often this also implies a new strategy for the customer, especially if the customer is an OEM. Once the business cases and use cases are clear, it's followed by data collection, data verification, model development, and deploying the solutions into the existing OT and IT landscape. Our software, APM Studio, is used at different levels in the automation pyramid. It can run embedded, which typically is the case for OEMs, monitoring faults and risks in isolation to the asset. And an asset can be instrumentation, process instrumentation, an actuator or a pump, a compressor, filter, etc. OEMs often use our software APM Studio as a basis for their remote monitoring services solutions at the device, edge, and cloud level. At the edge level, APM Studio typically processes asset data of one or multiple assets to run condition monitoring and predictive applications near to where the data is generated, enabling horizontal integration across assets. But we also work at level 2 and level 3 in the automation pyramid, where APM is used to monitor faults in relationship to the process, deployed or running on on-premise compute. When we deploy at level 4 and level 5 in the automation pyramid, APM Studio is used for optimizing the maintenance cost and planning associated to an asset base that supports a variety of different assets. We serve two types of customers. We serve OEMs, original equipment manufacturers, where we help them to maintain the margin on their products they bring to the market and allow them to create and integrate diagnostic and prognostic capabilities from their assets into their systems of their customers. We also enable them to provide new digital business and services models on their assets. In short, to stay relevant for the customers. But we also work for asset owners, the process owners, where the challenges around lowering costs, energy, and maintenance costs are typically the focus. Reducing the amount of planned maintenance and reactive maintenance, and of course enabling them to stretch the asset lifetime while balancing the risk and optimizing their planning at the same time. Now, OEMs see their asset as the value. The asset owner is quite different. They see the asset as a element that supports their process and their output. So they're different customers in that perspective. But for these customers, we can onboard them with the same software suite at different levels, from chip embedded to edge to on-premise to cloud with one software suite. So why do we do what we do at UReason? Well, around 95% of the data from instruments, machines, and processes is not used today to optimize maintenance. This is our understanding from hundreds of conversations with operators and manufacturers. And the operational data from processes and instruments is used, of course, to control processes, monitor processes, run processes safely, but very often not to optimize asset management or work processes and support maintenance in the most ideal way. This is our driver. This is why we help asset owners and OEMs to achieve more potential from the data that they already have. And we do this with a lot of passion, of course. Now, in today's webinar, we will have a look at what value you can get from the data that is stored in your process historians. Value towards doing real-time condition-based and predictive maintenance applications. And in order to do that, I will first address the question why we need to use the data from the process historian. Then I will detail what data we need. And following this, we will have a look at how to turn this data into value. And of course, there's also time for Q&A, but be aware during this session, during the webinar, I will also ask you questions. Okay, so let's start with your data historian. Your data historian is typically used to store important analog and digital values from the process that are of importance to safely monitor and control your operations. And most of the times, there's also data stored in there to audit your operations at a later point in time. You may have access to your data historian at the PIN, the Process Information Network level, or the level 3 layer, or you may have access to your historian via DMZ. There's also the concept of enterprise historians that we very often encounter at customer sites. And these are typically available and accessible at level 4, but often only contain a subset of the data of the lower level historians for accountancy and benchmarking purposes. So just to highlight, I hope you can see my mouse okay. So we typically have a process historian supporting operations at level 3. In a DMZ, we may have a copy of the process historian supporting other requests for time series data. And sometimes we very often see at the larger corporation that at level 4, they also have a copy of the historians for other purposes, benchmarking, accountancy purposes, in which there is only a subset of the data available compared to the historian located at the process level. So the first question to ask is, why do we want to use data from the process historian to support maintenance operations? Well, maintenance operations are becoming more and more data-driven for a number of reasons: optimization, cost driving, and of course availability to skilled personnel. And the data that is stored in process historians can help you in continuously monitoring the performance of your assets and may indicate, for example, improper usage, energy losses, and can help you build other use cases. But the data that is stored in the process historians can also assist you to see how operations influences the integrity of the asset. So what we do at UReason, you have traditional condition monitoring, which is using, for example, ultrasonic sensors or acceleration sensors that allow you to make a picture of the now current performance and dysfunctions of a specific asset, like we see here on the left-hand side. They are creating a picture of the now current condition of an asset. Using the data in the process historians, you can move towards continuous monitoring of your asset performance. And if there's sufficient data, I'll come back to that later on, you can also move towards preempting specific failures and specific issues with your assets and knowing that ahead of time. Now, the data that is stored in historians can support maintenance operations to know where they are on the PF curve, and to give them an understanding of how much time there is before a breakdown or a disruption occurs, and allows you to do possible interventions. For this, you need to know what the different failure mechanisms are of your assets. Typically, we get those from an FMEA or an FMECA. You need to link those to data. Data that is already available in your data historians. Sometimes we need to unlock additional data. It allows you to determine the P, the potential failure, which if you have data stored and data available, then also allows you, using techniques such as survival analysis, to determine what the time span is from the potential failure, and there could be many potential failures on this curve, to the actual failures, such that you can plan maintenance activities ahead of time, keep the integrity of your assets at the highest level, and make sure that you are not influenced by any disruptions or any upsets. Now, using the process data allows you to provide early detection of fouling, asset degradations, so you can prevent upsets. But the data may not always be used because there's also silos of data and data access in your organization. Now, before I continue, let me ask you a question, you the audience, just to understand if you're currently using data that is stored in process historians for asset and process performance management activities. So I'm going to launch an interaction which will pop up on your screen. The question is, do you currently use data that is stored in process historians for asset and performance management? And there's a number of answers. You may currently use it. You may only use data that is stored in the process historians as and when there is an upset, an incident, for investigation purposes. You may use it, but not use it very frequently. So from time to time, upon request, maybe not even when there is an upset or an incident. Or you may not use it at all because you don't have any access to the process historian. So let me just wait for your answers to come in for a few more seconds. So the majority of you is using the data historians, but not frequently. So you could say haphazard as and when needed, but there is no tendency or standard procedure to use the process historians to evaluate asset and process performance. Some of you, 21%, do not have access to the process historians. This is something that we see and encounter also quite often. That's typically because there are silos within the organization. Some of you, also 16%, uses it quite frequently, and the same percentage, 16%, uses it when there is an upset or an incident investigation. So overall, 32%, the most votes of the audience, you use your process historians, but not frequently, i.e. infrequently. And it can be quite of a value because using the process historians, you can, for specific failure mechanisms, detect the potential failure. And then when you can detect it, you can also start preventing it. Of course, you need enough lead time in order to prevent it. And we see here on the slide on the right-hand side an electrical submersible pump, which has skill deposits. The skill deposits actually reduce the performance of the pump. Also require the pump to be pulled from the hole in this specific case, in order for it to be maintained. And these are things that you can see based on the discharge pressures of the pump, suction and discharge pressures ahead of time. So the data that is stored in your process historians can be of immense value to detect, but also prevent process outages, process downtime. Now, to successfully set up a condition monitoring, real-time condition monitoring of predictive maintenance program, you need access to three categories of data. You need process data, historical data from your processes collected by your SCADA or DCS system. You need data from your enterprise asset management systems or CMMSs, maintenance management systems, which contain historical records of work orders, inspection orders from maintenance. And you can get these from systems like Ultimo, Maximo, SAP PM, etc. And the third category that you need is failure data. But of course, as an asset owner, you try to prevent failures from happening. So failure data will not be present quite a lot. So what we typically look for is the data that identifies the existence of failure mechanisms. Now, in this webinar, we will focus on the first, historical data from your process historians. And when we talk about historical data, data is actually data, analogs and digitals, as well as events, events and alarms from your systems. Now, not every data historian stores these, depending on how it's been configured and been set up, but these are quite valuable data sources as well. So there are many traditional process historian vendors, such as OSISoft PI, Aspentech IP21, Honeywell PhD, Yokogawa Exaquantum, Wonderware Historian, etc. And most of the traditional process historians use open databases, mostly Microsoft SQL Server as a backbone. So it's easy to get your historical data. And again, when I say data, it's process data, analogs and digitals, but also alarms and events. It's easy, of course, to get to the data, provided you have the right access rights or someone that has the right access right that can collect the data from the databases, from the time series databases. There's a few things to keep an eye on when working with the traditional data historian vendors. They apply compression techniques in these traditional databases, which could lead, for example, to aggregation of data. Aggregation meaning that data that is, for example, collected at a higher frequency, let's say once every 100 milliseconds or 500 milliseconds, is aggregated to a 1 second or sometimes a 10-second or a 1 minute basis. Aggregation actually provides you with a different view of what actually happens. So keep in mind when you're using the traditional process historians that you understand or have a good understanding of how the data is processed and how it is stored in the process historians. Next to the traditional time process historians, there's also a number of new kits on the block that store time series data. One of them is InfluxDB. That's one that's quite popular. But there's also Cassandra, PipelineDB, and Prometheus. And these new kits typically store all the data, and they provide aggregation functions on top of the stored raw data. Now, let me ask you a question again to better understand what process historian you currently have at your site. So I'm going to start another interaction, which will run for a minute or so. And if you could let me know what type of process historians you are currently using at the site. And I'm expecting, prejudiced, that OSISoft PI is the lead. That's why I also put it in the top. And we very often encounter OSISoft PI. But IP21, of course, especially on Emerson systems, Emerson DCS, we see those quite a lot. Wonderware Historian we see in the SCADA market, of course. But I also see there's about 10% of the audience, and it's going up a little bit, is using InfluxDB, which is really cool to see. That's one of the new kits on the block. Some of you, about 20%, don't know exactly what process historian is used, and I suspect that these are also the people that don't have access to the process historian in the previous question. So in the audience, I see OSISoft PI, the lead. About 30% of the audience is using that, followed by Wonderware Historian, about 15% of the audience. And about a third of the audience is not clear as to what process historian they use because it is not visible to them or not obviously visible to them. And the answers are still coming in, so I'm going to wait a few more seconds. And again, Cassandra, Yokogawa Exaquantum was not chosen by anyone. Cassandra we encounter from time to time, but predominantly in the discrete industry. And Exaquantum, which was one of the options as well, is a historian linked to the Yokogawa DCS. So I'm assuming there's no Yokogawa customers in the audience at current. Again, thanks for your answers. Now, typically when you have access to your data historian and you want to have access to your data historian, you want to do that for a reason. Sometimes you may want to do undirected searches in the data to explore the data set or to find patterns of interest. And you probably do this when you are a frequent user of the data historian, a frequent user, a user that on a daily basis looks at what is happening out there in the process, what is happening to the assets. Now, directed search is the most common usage of process historian. Directed search, you're looking for something specific in the data set, and maybe you're looking for a process upset or an increase in energy consumption, or you're looking back at what has actually happened. Now, when you do directed searches in data historians, we typically apply a method called CRISP-DM. CRISP-DM provides us a structured approach, and the customers as well, to analyze the data geared towards a result that you can put online. So using the CRISP-DM method, you need to understand the reason why you're using the data, directed search, so there needs to be business understanding. You need to understand the data that you're evaluating. You're evaluating it, for example, to detect certain degradations or failures of interest. And then based on the data, if you're interested to, for example, understand where you are on the PF curve, the failure curve for assets, then you start doing directed searches around certain failure mechanisms that you would like to detect from the data set. This is a very typical approach that we apply where there is knowledge required about the business and the data, and also knowledge required about how to then deploy that model and data. And we typically support our customers in this process, which up to the point of step number 6 here, is typically done in analysis tools that are used by domain engineers or by data scientists, such as KNIME, RapidMiner, SPSS, SAS, Python, H2O AI, different types of platforms. And I will also show and demonstrate one of these platforms during the demonstrations. Different types of platforms that allow you to work on the data, manipulate the data, do a feature selection, train models, and make models ready for deployment. Now, when you're ready for deployment, we have a mechanism of deploying models inside APM Studio called PMML. That's a standard body that has been out there for a few decades, which has defined a standard for allowing you to make your analysis results deployable. So analysis you do on historical data, not in real time. And once you have trained a model, let's say, and validated the model to recognize a certain type of event, P on the PF curve, you want to deploy that as well on your streaming data. And using PMML, we can actually do this. And I will also show this later on in the demonstration. I will first show the analysis environment. So the left-hand side here, training a model, investigating data, then exporting my result as a PMML, and then make it runnable on the live data. Okay, and I'm seeing some comments here of people using different solutions. Ferry is using Inmation. I see Canary there. Inmation is being recognized. InfluxDB as well. So thanks, Ferry, for contributing to that, and Peter as well. Now let's have a look at an example. I have data and functional degradation data from various process equipment in my plant. And this functional degradation data is based on data from process historians and maintenance management systems. Now, looking at the process data, I do not see a clear picture or a clear relationship between the various pressures and the temperatures and the flows that are being measured in my process. So we see the P is the pressures, T is the temperatures, there's flows, and there's an efficiency, and the performance of a specific asset being calculated. And we don't see a lot of changes to the efficiency nor the performance, but we do see quite big jumps in the pressure and temperature profiles here in this system. It's a cooling system in this example. Now, if I look differently at this data set, so if I investigate this data set only from a viewpoint of finding singular pair correlations. So singular pair correlations are the different properties that I have in my data set compared to each other, but not compared to multiple sets of other parameters. I do see that there are some very heavy correlating features. So we have negative correlations. One value goes up, the other one goes down, a negative correlation. And we have positive correlations, the blue. And let's have a look here at the cooler condition. I can see, for example, that my cooler condition listens very closely to the temperatures inside my system, which is kind of logical. So there is a negative correlation between the temperatures in my system being warm and inverse being cooled, and being represented by the cooler condition here. And there's a few positive correlations here as well between the cooler condition and some of the pressures that I have in my system. I also have a number of values that do not correlate well at all. And bear in mind that you should not look here at the diagonal line, because the diagonal line will always be the same feature, the same column in my data set compared to itself. So that will always have a positive correlation moving together, so to say. So I need to look at my data in a slightly different way in the relationship that the different features have together. And I can use, I tried for this specific system to formalize a formula that can actually help me to understand the status of my cooler condition. But it's not possible because there's a lot of different variations. So, and it's very nonlinear. So in this case, one of the possible ways to solve this is to apply machine learning models that I can use to classify or recognize the fault that I'm after. So for the cooler, but also for the valves and for the other assets in this example, I have different failure classifications, and these different failure classifications I can use to, with machine learning techniques, to determine or to tell me what the remaining useful lifetime is of my coolers, so that I can take the appropriate actions. Now, machine learning is hyped to an extent that I'm sometimes not very happy with. So I would like to share with you in one slide, two slides, the basic concepts, but also the important concepts, the important things to bear in mind. So there's different types of machine learning. And there's the type of supervised machine learning, and you compare supervised machine learning to telling an algorithm what the expected outcome is. So you can compare supervised machine learning to taking driving lessons, and you have a tutor sitting next to you in the car. In most countries, not in all countries, but in most countries, that will tell you how the clutch works, how the brake works, how to accelerate, how to indicate when changing from lanes, etc. So you have someone telling you what the requested action is and the expected outcome, and also helping you and steering you in the expected outcome. So supervised learning is training with a trainer. And the opposite of supervised learning is unsupervised learning. It's a machine learning technique that allows you to find structure in data. So unsupervised learning is typically used to find structure in data, or to find a normal operation mode in data. And unsupervised machine learning models will tell you the moment that normal operation is not the case anymore, that you have a deviation from normal operation. So making the analogy to the driving lessons, unsupervised machine learning is like handing you over the keys of the car, and you step in the car. You may step into not the driver's seat, but maybe in the passenger seat, and you have to try and figure out, go along and find how the car actually drives, how to accelerate, how to use the clutch, etc., etc. So it's a very different technique. Supervised machine learning is the most common technique that we apply in the domain of asset performance management, because it allows you to classify where you are on the PF curve. So it allows you to classify the specific failure mechanisms for different assets and for processes. And it allows you to then also determine the time to event, so the amount of time that you have until a potential failure occurs. So supervised machine learning is the most common used approach that we have in industry. Now, there's a few other examples. You have semi-supervised learning and there's reinforcement learning, but these are techniques that you typically don't apply in the operational domain, but you apply in R&D type domains. It's not something that we do in the process industry. So just to summarize this, or put it very simply, supervised machine learning training with a trainer. The algorithm is provided with the outcome to recognize this outcome in the data that is not seen. The very opposite is unsupervised machine learning, which is useful for both recognizing groups and deviations from what is trained to be the normal operation. So supervised machine learning, training with the trainer, understanding the outcome. So you could use them for soft sensors. You can use them for recognizing a specific failure class. Quite powerful, used in many different areas. unsupervised machine learning, understanding structure in the data and seeing the deviations from that, from a normal operation or an operation that you've trained or labeled to be normal. Now, let me take you through a demonstration. So in the demonstration, I'm going to have a look at the data that I have of my pumps, valves, and coolers, and show you how I'm using the data. I'm doing some pre-processing on the data, and from that, I will also then jump to how we can actually make this live. So I'm going to switch. Well, switch is the wrong word, but I'm going to move my screen over here, maximize it, enlarge it a little bit because I think it's a bit small. There we go. So I have, as we saw in the slides where I had the different pressures and temperatures, cooler conditions, etc. I have data sets, different data sets. I have labels that are indicating to me different conditions of my valves, my pumps in my systems, my coolers, etc. So the label data could be data that is extracted from, for example, inspection results, or which is being put in by a domain expert. And then I have different analog data, vibration data as well, from my process historian at actually at different frequencies. So for example, here I have data that is measured every 100 times a second, so at 100 hertz. And I have multiple data sources that are of a different granularity. So what I'm doing here, I'm doing a lot of pre-processing. A lot is relative. I'm doing some pre-processing on the data, and I'm joining the data that comes in different granularities, different scan rates, together into one main result, the joint table. Let's have a quick look at that. The joint table is, and my eyes are going by this, it's about 13 million rows. So I have 13 million rows of data of pressures, temperatures, vibration, etc. From my data historian. So it's quite a lot of data. If I would give this to a statistician, he could tell me things about how the data is distributed. Maybe he can pop up some trends, etc. But yeah, as we saw earlier, just using the trend data, I cannot say if I'm going towards an issue with my coolers or if the coolers are still okay. It's quite a lot of data, and it was also very nonlinear, so it wasn't easy. It's not easy at all to have a formula that expresses my cooler conditions. So what we've done here is we have multiple streams here where models have been trained to recognize certain conditions that are present inside the data. And this is supervised machine learning. We also saw earlier that I showed a correlation plot. So here we have the same correlation plot. Let me just make this a little bit bigger for you. This is, well, I was going to say this is better readable, but not all of it is better readable. So we have the different pressures and temperatures, and this data has been anonymized. Cooler conditions, valve conditions, etc. And we can also zoom into, if I hover over one of these cells, the specific correlation coefficients. Tells me something about the relationships of the data, so about which features to select from the data set to predict a model, or sorry, to train a model that can predict my cooler condition. So here we see all the variables that are available. I should neglect this one. And here again, we can see the different correlations. And based on probably these 6 features here, so the pressures and the temperatures in the loop, I can predict my cooler condition, or I should be able to train a model that can predict the cooler condition. So the training of the model, we have a valve model here, we have a cooler model here, is actually done here at the bottom. Not all the columns are put forward for training, so I'm only taking forward some of the pressures and some of the temperatures, plus the actual cooler condition and the cooler efficiency, which we see here is quite stable. Cooler condition has different labels, numeric labels in this case, to express if the condition is good, medium, going towards a failure, etc. So there's labeling that took place inside this data. The total data set, so we saw, and I can click on this guy again. If you look at the filter data, we have 13 million rows of data. I'm applying supervised machine learning here with a neural network. I don't want to feed or don't want to supply all the data to my neural network and then deploy that neural network, because I would very likely overfit the solution. No, I'm partitioning the data, so I'm handing over 70%, that's the ground rule of my data, using a certain random draw or stratified sampling to my neural network for training purposes, and 30% of the data was never seen by the output of this block. So a neural network is trained, and the neural network has been trained on a portion of the data, in this case 70%. And then this block actually allows me to validate the model that was trained here on the basis of data that is never seen. And that's really interesting, because if you have a good validation result, then you have a model that you may also want to deploy in real time, and you deploy and update, etc. So I just clicked on, and this view is popping up on the wrong screen, so I'm going to move it over. So I clicked on the view of the scorer block. I have three different statuses of my cooler condition. It's going towards failure, 20, which still allows me to take appropriate actions. In failed condition, and it's in a perfectly okay condition. And here we see for the different data samples that were fed for validation purposes, so the 30%, how good the model actually behaved. So from the data that was actually in good condition, it predicted 99.26% to be in a good condition. So we're off by 0.74%, which is quite good. Of the data that was going towards failure, that's the one I'm interested in. It's also predicted with a quite high accuracy, actually a little bit higher even, 0.5% roughly is off, which is again very good. And of the failure data, I get a little bit lower accuracy here, but 3% of the failures were not properly recognized in the data. So overall, the overall statistics, or the overall accuracy basically of the model that was trained here in this analysis environment is pretty good. And just to point out, you can do this yourself as well. The environment that I'm using is KNIME. It's an open source environment. If you would like to train a neural network on data that you have labeled and you would like to validate that, it's quite easy to use. It's click and connect and configure, same as APM Studio. Yeah, this one is not connected yet, but let me show you in this guy. Each block basically has a X number of configurations. The system also helps you in setting up these flows. And there's also the capability inside this tool, KNIME, but also other tools, to do a thing called AutoML. AutoML is automatically training your models on the basis of the data. So the software is going to suggest to you what the best fitting model is with the right tuning parameters, but also provide you with the model. Now, I'm interested also to make this runnable. So one of the things I have here is a thing called a PMML writer. So the output of this model, and I'm going to show another screen now, is actually a predictive model markup language file, which we see here, which basically declares to runtime environments like APM Studio what the different properties are, the different data elements are that it needs to evaluate. And it tells the runtime environment APM Studio that it's a classification model. It tells it how to normalize the data. It tells us also what the target is. At the target, I'm interested to predict the cooler condition. And then down here we see basically the build-up of the neural layers in the neural network, which is instructions to the runtime engine APM Studio how to run and execute this model to come up with the right outcome. The right outcome with 99.4% accuracy, roughly. So PMML is actually the bridge to my next demo. And I see that I need to hurry up a little bit. I've taken too long, but bear with me, bear with me. This is APM Studio. So in APM Studio, it's an environment drag and drop like we saw just before. We have an environment to connect to data, define meta models, define object models, or read them from databases also. Define standard alarms, key performance indicators, state models that identify certain processing states of your processes or assets. Define processing rules. That's one of the things we're looking at right now. But also build dashboards, cause consequence models like bow ties, complex event processing rules that allow you to correlate events over time. But in this webinar, it's all about using the data from your data historians in an effective way. I have a model on my cooler, which is continuously running this machine learning model that we exported. So in here, I just opened it for the details. We see it's live, so it's receiving from the field, anonymized, the different pressures, temperatures, etc. And on the basis of the model that was trained in my analysis environment, I'm predicting what my cooler condition is, such that on the basis of that cooler condition, I can take the appropriate actions. So this PMML model that we see here is running model.pmml. This is the neural network that I was showing earlier. So it's doing the calculations on basically the propagation of the neurons with multiple hidden layers on the basis of the way in which my model was trained and validated, and it's calculating the likelihood of failure, the likelihood of reduced efficiency, and the likelihood of full efficiency. 100% okay is full efficiency. And inside APM Studio, you can see this arrow here. It's a graphical environment. We have palettes with different functional blocks for doing running PMML models, but also running fuzzy models, doing control as well, which we do in the field obviously as well, and defining different processing rules to process the data to come to meaningful results. APM Studio is, you can see, completely web-based, comes with a lot of examples, a lot of online help as well, just to point out to you. So if you would like to, for example, build a machine learning model and integrate this into APM Studio, which we just did, or connect to data sources from process historians, or to an IIoT platform, or to a maintenance management system, there's many different examples which are also runnable with inside APM Studio that you can click and follow on a step-by-step basis. I see a question from Lars. If you want to train a model to recognize certain degradations and dysfunctions, how much data do you need? It's a very good question, Lars. So the amount of data that you need, if you want to train a classification model on different failure mechanisms, and you only have one occurrence of a failure mechanism, not a failure, but a failure mechanism, it's insufficient. Training models at the end of the day is statistics and math, and you need to have a certain volume. So depending on the case, let's say you have 1,000 records of data, 1,000 rows, and you have 500 good ones and 500 bad ones. That could already be sufficient data to train a model that has a high enough accuracy to predict a certain failure mechanism. And you very often already have that data. But you need to keep an eye on the accuracy. So how much data do you need? If you have your process historian, you have 3 months worth of data, you have FMEAs and FMECAs, you're ready to go. And I think most of you in their process historians have 3 months worth of data. Now, in that 3 months worth of data, you may not have, of course, all the failure mechanisms that you're interested in, but you can start with as little as that. I hope that answers the question. And I just need to peek at the presenter chat. Answered. Okay, cool. Okay, so there's many different examples here. In the examples, we're also using NIME because it's an open source tool and you can use it. This is an example that predicts the oil quality. oil quality is sampled from time to time. You don't want to rely on those lab measurements, so there's other ways to also get to that data. So APM Studio, quite a rich environment, for looking at your data, setting up dashboards, getting insights into asset performance. We also have a lot of what we call typicals. So, for example, here we have a typical of a pump. For the pump, you have related to the pump the discharge pressure, suction pressure, RPM. On the basis of this, we can calculate net positive suction head, efficiency, total dynamic head, etc., etc. So, APM Studio comes with a lot of built-in capabilities that allow you to build these dashboards quite quickly as a domain expert. Just to show you, like with the processing rules and many of the other elements inside APM Studio, graphical or guided interfaces that allow you to set up property displays on the fly. Okay, let me switch back to the presentation, and give me a second to do that. There we go. And I need to hurry up a little bit because I'm running behind. Let me ask you a question again. And I'm just getting the integration panel. Have you started, or do you want to start with a CBM or PDM program using advanced analytics techniques? So I just showed a platform, an analysis platform that you can use. You can start using today. That allows you to analyze your data, but also train and validate models. You maybe are using Python or some more script-based languages, but there's also, let's say, more domain engineer centric or friendly, I should say, environments that you can use. So I'm just going to wait a moment for your answers to get in, and I'm going to take a small sip of my coffee. So I think the majority of you wants to start, about 50%. It's good to see. Some of you, about 14%, want to start but don't know yet where or how to start best. Some of you don't know yet, are still exploring. And there's about 20% of the audience has already started. That's good to see. I think yeah, a lot of companies and of course people within the companies are still looking where and how to start best. I think the good news is I've been in this field of using this type of AI techniques for a very long time. The good news is that the level of knowledge that you need to have of using these types of systems is becoming the systems are becoming more and more usable and user friendly. I mentioned earlier on AutoML. You can also have the system predict and present to you what the what the ideal outcome is. So let me just this is just a summary slide. There's also some slides in the presentation deck that basically summarize the demo that I gave as well. I've already showed APM Studio. So within APM Studio, the exported PMML model. So you have an analysis environment. It can be Python, SPSS, SAS, many different analysis environments. In those environments, in most of them, you can export your model to PMML, predictive model markup language, which can then be made runnable inside APM Studio. And let me ask you a question again about bringing analysis results online. If you were in a position to take data from your process historian and provide early detection of certain unwanted events, would you be interested, or would you then take your analysis results online, or would you still use your process historian to do in hindsight analysis, i.e. looking after the fact why things have actually happened? And if you want to bring them online, are you ready? Do you already have a solution, Databricks with a data robot or other environments? Are you looking for solutions, or maybe it's not relevant at this point at all? That could also, of course, be the case. Or you're not looking to bring your results online. And I'll wait a few minutes for the audience to respond. And there's still a lot of answers coming in. And about 44% of you are looking how to bring analysis results online. For some of you, it's not relevant right now. Some of you, 20%, already have a solution. I think actually it's now 50% are looking how to bring results online right now. This is one of the areas where, in my opinion, there's not a lot of attention. AI and machine learning are very often put onto one pile. It's not the same thing, not the same beast. It's different. AI is an umbrella concept. Many different technologies fall underneath it: fuzzy, expert systems, Bayesian networks, belief networks, etc. Machine learning is a technique within AI. They're definitely not the same, but most of the AI initiatives, platforms, etc., are focusing on providing you with the analysis capabilities. When you go to making AI runnable, there's still a lot to be gained. Okay, and I'm gonna switch now to the Q&A session. I talked a little bit about the process historians, what data you require from your process historians, in essence, to make that data of value to your maintenance operations and operations. What different types of process historians you have, how to then treat the data if there's no obvious relationship in your data, how to treat that data with techniques such as machine learning to get value out of it, and how to actually take those models that can tell you ahead of time and take those online. So a bit of a summary. I understand that there was a lot of information in this webinar. But don't hesitate to contact me for further questions. Here are my contact details. There's 2 QR codes. You also get the presentation slides. So don't hesitate to contact me for further questions, examples, reference use cases, or discussing use cases, or to discuss how to do things differently in your industry. And I'm now going to switch back again to the video feed. So I've been here all the time, obviously. And I'm going to have a look at Carlos and see. And Eugenio is already leaving. Thanks, Eugenio. I really appreciated you being here. And I'm going to have a look at the questions. Let's see. The question from Lars was already answered. There's a question from Avan Paul. I hope I pronounced it correctly. Going back to the previous model, from the 70% of data that went to the ML block, how did the block know what the failure was? How easy is that to implement? Okay, so Avan Paul, sorry if I pronounce it correctly, is wondering how the block was able to predict it. So I'm going to make a quick switch back to my screen. I popped up Nime in here. Let me just share. Okay, so I can't do 2 at the same time, video and the screen, unfortunately. So we see here is the model that gets 70% of the data. In this configuration here, I'm telling the model, I'm telling the algorithm basically what my target function is. So the target function in this case is a numerical string. It's actually string numerical, which tells me about the cooler condition. So I have data, multiple rows of data, 30 million rows of data, which have also been labeled with the cooler condition. That's been done semi-automatically. And on the basis of the cooler condition, this model on 70% of the data will start training a neural network. And once it's done, it will hand the trained neural network to the predictor block. And this predictor block will get 30% of the data that this model has not seen to determine if on unseen data it can also be accurate. And so, how easy is it to implement this labeling? Quite easy, because you have, if you remember earlier on in the slides, I presented that you have different types, and I'm going to try to do that quickly. See if I can do that in this way. Move it up. Bear with me a second. I'm just looking for the right slide. There we go. Pulling it up here. So remember, there's multiple ingredients. We have the process data. We have the data from your CMMS or your enterprise asset management system. These two can already be combined to auto-label your data, in addition to other data sources that may contain failures and dysfunctions. Sometimes it's an OEE database. Sometimes it's RBI results. The failure data, or this failure data, the third category that's mentioned here, is the least structured. There's no you could say standards for that yet. But with these two data sources, which are available in most companies in large volumes, you can already start, and it's relatively easy to implement. Paul, I hope I answered your question. Let me switch back again to a question of Almar. What is the best way to prepare my data from my process historian for usage in the analysis package you showed? Okay, so Elmar, the analysis package I showed, I didn't show all the capabilities and all the features, but it has a number of data connectors that allow you to connect to different databases, allow you to connect to different files that contain data, such as CSV files, for example, or Parquet files, etc. If you use Parquet. So if you currently have a process historian, I can't see from your question which process historian you have, but let's assume you have OSISoft PI or you have Wonderware Historian. I think that those were the most selected in the earlier questions. You can make a database connection directly to OSISoft PI and pull the data from the data historian. I would advise against that. I would do one batch download of the data from your process historian. Depends, of course, on how big it is, but take a few 100 days or a few gigabytes, depending on what you need from your process historian. And there's different data connectors in KNIME, the tool that I showed, to connect to data sources, databases, general databases. Plus, there's also data connectors inside KNIME. It's quite a versatile platform to connect to Hadoop, Cloudera, and other types of instances that may contain data in a less structured way. So there's multiple ways to connect and then also prepare and analyze your data. If you like, Elmar, I mean, we can have a session on what the options are and what the different variants are that you can take. Then there's a question from Jaime. And he's asking if we're working with performance forecasting. And Jaime is working on an RNN, a recurrent neural network. You didn't, that's interesting, like LSTM networks. But the models are difficult to train. I hear you, Jaime. Yeah, so performance forecasting models, at the end of the day, performance, I don't know how nonlinear your system is using RNNs. So I assume that it's quite nonlinear. These models are more difficult to train, correct. You need to have sufficient amount of reference data. So earlier on, there was one question that asked, how much data do I need? You can already start with 1,000 rows. The type of thing that Jaime is trying to do, if I pronounce your name correctly, Jaime, is to do performance forecasting using a technique called with recurrent neural networks. It's slightly more difficult, but still doable. You need a higher volume of data. around 10K. It really depends. Maybe we can discuss the specific use case, Jaime, but um, the models can be more difficult to train because the nonlinearity in the models is more intense. Maybe one of the things Jaime to do, or not to do, but I suggest, is to look at support vector machines, because they can also, so SVM, they can also be used quite well for working with a very nonlinear domain that you're currently working in. I'm assuming you use in a nonlinear domain because you're using RNNs with a lot of unknowns. Interesting approach though, LSTM. One of the things, the data set that I showed earlier, one of the guys that worked on the data set also started with LSTM, but it wasn't the right approach for that specific data set. But good question. Thanks, Jaime. And I'm just having a look. Ariandi, thank you also for attending. And Jan Willem, thanks also for attending. I see a lot of thanks. I'm just having a look at the presenter chat. If there's any more questions, there's no more questions. I went 6 minutes over time. I apologize. It's always a bit of a challenge to keep it in the hour. But I really appreciate doing this. I hope you also like it. Start of the year, January, so we'll go back into the cadence of doing one every 3 to 4 weeks. Ferry, also, thanks for attending. And I think this ends the webinar. If there's any more questions, Saber also, I see all of you coming by now. Thanks for attending. Um, um, if you have any questions, reach out. Don't hesitate. You have my email details. And oh yeah, forgot about that. Thanks, Carlos. We really appreciate your feedback as well. So if you can leave your feedback once I stop the webinar, you will get a pop-up screen. It takes less than a minute to fill out, but in the pop-up screen, there's a number of questions about how you experience the webinar, where we can improve, etc., etc. Again, thanks for attending. Mohammed, also thanks for attending. And I'm going to stop the webinar so you can fill in the evaluation sheet and let us know what you would like to have addressed as well. And I'm definitely sure that we'll have time in the next webinar to do that. Guys, take care, stay safe, and stay healthy.